This is Juno 7, question 4a, part 1. What is a stationary wave? So a stationary wave is something where you have got two waves which are interfering with each other and there's no energy transferred as a result, whereas in a progressive wave, the wave transfers energy from one place to another. So in the mark scheme, all they're looking for is a wave where no energy is transferred. So the result of any energy in the wave is that it cancels each other out. The energy due to amplitudes and troughs cancel each other out. What conditions result in the formation of a stationary wave? So there's that question again. We only need 2 marks, but what you need is you have 2 waves travelling in opposite directions and they have to have a constant phase difference and they must interfere with each other. So 2 waves travelling in opposite directions interfere and they must have the same frequency, or you could say a constant phase difference, or you could say that they are coherent, which means the same thing. State the physical principle required to explain the formation of a stationary wave. Now what they're looking for here is the word superposition. Okay, B part 1, figure 4.1 shows a string of length 0.6 meters held tight between 2 fixed supports. The string is plucked at a point X halfway along the string as shown in figure 4.1, which is this one here. On figures 4.2 and 4.3, draw the first 2 modes of vibration of the string. Mark the positions of any nodes N and antinodes A. Now, something I didn't realise, and I had to find this out, is that if you pluck a string in the middle, it forms an antinode. So the first mode of vibration for that idea is this fundamental frequency one, like this. And that's absolutely fine. So there's your antinodes. And there's your nodes there. But on the second one, it's tempting just to do your pattern with 2 loops on it. But you must have an antinode in the middle, so you actually have to go to the third pattern. Like that. To get an antinode in the middle, because that's where it's plucked at. And that's your pattern there. Part 2, calculate the wavelengths lambda and lambda 2 for the first 2 modes of vibration. So if we look back here, you can see that you have got half a wavelength, and that's equal to 0.6 meters. And here you've got 1.5 wavelengths, and that's equal to 0.6 meters, that distance. So we transfer those over here. We have got lambda over 2 equals 0.6 meters and 3 lambda over 2 equals 0.6 meters. And that will give you a wavelength of 1.2 meters there, and then 2 times 0.6 divided by 3 is 0.4 meters for that one. And part C. The string stops vibrating. It is now plucked at point P, 0.15 meters from the left-hand support as shown in figure 4.4. Remember, it's got a length of 0.6 meters. Draw the first mode of vibration of the string when it is plucked at this point. Now, again, there has to be an antinode in the middle at this point P. So you know that that's actually a quarter of the length of the string. So that means that you would have one complete loop there, like that, and then obviously you'd have one more there. So calculate the wavelength lambda 3 for this mode of vibration. So lambda 3, then you've got 2 loops or 1 complete wavelength, and that's equal to 0.6 meters. So answer is 0.6 meters down there. So I hope you understand that. if that's 0.15 metres and the whole string's 0.6, that's a quarter of the way down, and this has to be an antinode here, and therefore to have one complete loop then that must be 0.3 metres in total, so you've got space for 2 of those in your string.